Becca Willett is our next speaker. Becca is a professor of statistics and computer science at the University of Chicago. Becca received her degree in electric and computer engineering at Rice University. She then became a professor at Duke University. She then became a professor at the University of Wisconsin in Madison, where we missed each other. And then she joined the University of Chicago in 2010. Becca has received a career award from the NSF, a DARPA Computer Science Study Group Award, an Air Force Scientific Research Young Investigator Award. You get the picture, many of them. And recently, he was named Fellow of the IEEE in 2022. At the university, she's one of the leaders of the Institute for the Foundations of Data Science, the Air Force Research Lab and University Center for Excellence in Machine Learning. And of course, she leads the University of Chicago's AI for Science initiative. And we're going to give her a big round of applause because she's the main organizer of this conference.
Thank you very much. It's a great pleasure to be with all of you here today. When I was a graduate student, one of the things that I was working on was medical imaging. And one day I was at the hospital to talk with a collaborator, and in the elevator they had this sign and it said, if you will participate in our fMRI study, we'll give you a CD with all of your brain data. And I don't know anybody in this room who would pass up on this, and I certainly didn't. So I signed up for the study, I went in, it was really fascinating, I learned a bunch, it was a lot of fun. But then a couple of weeks later, the PI of the project gave me a call, and he said, you know, we actually can't use your data because when we did the scan, we found a tumor, a meningioma. So we said, you need to go get a clinical scan and talk to a neurosurgeon. And I did, and they did remove it and everything was totally fine. There's a functional neural network somewhere in there. But I was thinking about this story as I was preparing for this conference, because really AI is going to affect every single step of this process. AI is going to change the way neuroscientists design their experiments, the way that we have systems like this acquire the raw data, the way computers reconstruct images for radiologists to examine, the way radiologists interact with those images using computers and machine learning to help make sure they don't miss anything important, the way that neurosurgeons assess patient risk and decide whether something's an incidental finding or something really worth the risk of surgery, how neurosurgeons conduct surgery using robotics and advanced imaging techniques, and even what kinds of medications are prescribed after the fact. And healthcare and examples like this are not the only ones that are going to be transformed by AI. So we asked everyone at the beginning of this workshop to think about where are the areas where AI could really have the most transformative effect and impact on people's lives. And people have told me all different kinds of ideas all week long. Things like developing a new understanding of the laws of nature and the rules of life, accelerating affordable drug development, engineering green materials, building quantum computers, and developing sustainable climate policies. So what is it going to take to make these things actually happen? So we had this really fascinating talk by Rick Stevens to kick off the conference. And Rick posed and answered this question. He said, what's the best use of really powerful, large-scale AI systems in the context of science? So once we've got really powerful AI, how should we best use them? What I would like to do today is to pose a complementary question, which is, what are the AI and machine learning, oh, I know, I do not photograph well. What are the AI and machine learning advances that are needed to realize these science aspirations? So we've certainly have heard people say, well, we certainly need more scale, more computation, more data. And I certainly agree. But I think there are also lots of opportunities for, as Max put it, for us to be smarter. And this is very domain dependent. And so the primary thesis here, that what we've been talking about all week across all these different disciplines, is that AI and machine learning are transforming science. And investments in the foundations of AI and machine learning are really essential to producing high quality, reproducible, AI-enabled scientific research. Okay, so what do those foundations look like? Well, that's basically what I want to discuss with you all today. And I've thought a lot about some of the key themes that have shown up across our talks in physics and chemistry, in earth science, and biology. And I think some of the prevailing themes that we've heard over and over again are uncovering new laws of nature, AI-guided scientific measurement, physics-informed machine learning, and of course, advancing AI foundations. So let's unpack these one by one. The first one is uncovering new laws of nature. And by that, I mean, given observations of a system, how can we use AI to uncover the governing physical laws? So to kick us off, let's take a look at this. I've got two particles here that are almost in the same location, and now they're going to start moving according to a Lorentz 63 dynamical system. And the equations of that system are over here on the right. They're just describing the change in the X, Y, and Z coordinates of these particles. This is a chaotic system, so even though the particles started in almost the same location, as things evolve, they get far apart at some points, and so the initial condition gives us little insight into where they're going to be down the road. And what we'd like to be able to do is to take data like this, the locations of these particles over time, and from that, figure out, in cases where we don't already know the equations, what those equations look like. And this is a problem that shows up in all different kinds of settings. So, we're trying to take this trajectory information and figure out what those equations look like. So Vincenzo gave us this really incredible talk yesterday, where he was essentially accomplishing this in practice, rediscovering or discovering brand new biophysical forces that help us explain cell development and function. We can also imagine these same kinds of ideas being applied to understanding the foundations of soft condensed matter and polymer physics. And with that understanding, we can build sustainable new materials. Another setting in which these kinds of ideas might be applicable is in trying to understand the dynamics of microbial communities. So we have colleagues who are trying to build microbial communities that can do things like break down plastics, or who can help the gut microbiome and have really substantive health impacts. The problem is that in a lot of these cases, they build up the microbial community, they set it loose in the wild, and then it dies right away. It works for a tiny bit of time, and then it just pitters out. And we'd like to understand, well, what are the dynamics? What are the properties of these communities that ensure that they will be long-lasting and will be sustainable? And then finally, we can even think about systems where there are lots of local rules that we understand, but we don't understand sort of the global emergent behaviors. And an example of this would be, for instance, agent-based models that were used to try to understand how humans figure out what those weights are. And hopefully we only need a small number of weights that are not zero, which is the case in this Lorentz 63 setting. So we get a simple and explainable and an interpretable model. And then we can repeat this for the Y coordinates and the Z coordinates. And all of a sudden we've uncovered the equations that govern the motion of these particles. So this is a nice idea. It's been used in many different applications, but unfortunately it doesn't really scale. It works well in these cases where we only have 3 dimensions to work with. But once we work with much higher dimensional systems, then these things start to break apart for reasons that are well explained by applied mathematics and statistics. And so ongoing and really exciting work in AI and machine learning. Something happened. Oh, okay. Is making progress in this space. So tools like AI Feynman and recent work by the Flatiron Institute rediscovering orbital mechanics laws from the motion of planetary data, as well as the stuff that Vincenzo told us about yesterday, are all examples about how modern AI tools and advances are helping us to discover these new natural laws. So the second pillar that I'd like to discuss is AI-guided scientific measurement. And in fact, Andy's talk just before mine was a great example of this in action. What I mean here is using AI to design better experiments, but also better simulations and better sensors. Okay, so for an example, I talked earlier about microbial communities. So let's say that we're talking with Sepa Kuhn, my colleague here at U Chicago, who's trying to design microbial communities that can help people improve their gut health. And what he tells me is that the problem is that they'll do these implants and then all of the bacteria will just die after a couple of days. And so people don't really have any lasting benefits. So what he'd like to be able to do is to measure the community fitness, some measure of how long it's going to last and how long it's going to be effective. So let's think about that fitness as some unknown function F with some unknown parameters theta. And it depends on what strains are in the community, what nutrients are available, what antimicrobial peptides are killing off the bacteria, and other environmental conditions. So we don't know this. And what we'd like to be able to do is to figure out what this fitness function looks like so that we can choose the optimal microbial community. So you might say, well, let's just try them all. And the space is just too large. There's basically an infinite number of communities to grow. So we can't possibly do that. And then you might say, well, let's just sample at random. But if we think about what that means, what it means is that we actually combine all the strains and the nutrients, we design the implant, we give it to a human, we then monitor them for several days or weeks, and then get a sense of whether it worked or not. This is a laborious, time-consuming, and expensive process. And so if we're just kind of randomly generating microbial communities and putting them in people, then we run the risk that we're spending all of our resources very far away from the optimal point that we want to be at. And so the kinds of ideas that Andy was telling us about and that AI can really transform this process involve using AI to try to understand what this fitness function looks like and then use that to decide what our next data should look like. So for instance, in my graphic up here, the black line is the true fitness function that I don't know. And let's imagine that I've got some rough estimate of what it looks like. And that's denoted by this pale green region. So I'm thinking that the fitness function is somewhere in there, but I don't know where. So what I would do at each time point is I would choose one kind of microbial community, some point along this path, where under the best case scenario for this fitness function, I would have the maximum fitness. So in this case, it's over here on the right. So I design that community, I implant it, I collect a measurement with a little bit of noise, and I use that now coupled with AI methods to update this model and to update my uncertainty in the model and get a new estimate here. And then I just repeat this process. I say, what's the best case scenario subject to my uncertainty about what this fitness function looks like? And it looks like the highest kind of upper bound is over here. So I'm going to build this community, collect a measurement, and then rinse and repeat. And this kind of process allows us to much more efficiently use our experimental resources when they're limited. And AI tools help us get really accurate estimates of these uncertainty bounds. So ideas like active learning, bandit methods, Bayesian optimization are all fundamental AI methodologies actively under development that can advance this kind of paradigm. This is something that Rick Stevens actually told us about during his talk on the first day of the conference, where he was talking about developing self-driving laboratories at Argonne and other places around the world. We also heard about these kinds of ideas in John Chodera's excellent talk yesterday afternoon when he talked about the design, make, test, and analyze cycle in drug development. So here they're exactly doing this. Every time they design and make a drug and then test it, they use that to decide what are the next set of compounds they're going to test. In addition to guiding the collection of data, AI can really have a transformative effect on data-intensive physics facilities. So we had Jesse give us a great talk yesterday where he was saying, you know, in the Large Hadron Collider, we might have these jets and we want to do jet tagging. We have to do it once every 25 nanoseconds. And we have other settings where we're just collecting massive amounts of data at huge velocities with gravitational wave data, astronomy data, neutrino data. And in these systems, we need to think about how to design AI tools that can be integrated into embedded hardware systems that can operate efficiently at scale and at the kinds of velocities that are required. And here there's another opportunity for algorithm development, for algorithms that are not commonly used for things like recognizing pictures of cats on the internet. The third pillar that I'd like to discuss is physics-informed machine learning. And by this, what I mean is optimally leveraging both physical information or physical models, as well as experimental and observational data. So what happens when we have both? It's not an either-or proposition. And this is something that happens in all kinds of applications and settings. So we've heard people talk about things like molecular structure estimation. And when we look at algorithms like AlphaFold 2, they're absolutely incorporating physical information, things like evolutionary information underlying the development of these proteins. And when we look at climate and weather models, there's a wealth of physical information coupled with our satellite and ground sensor data that we should be able to leverage. And in addition, we have advanced facilities like synchrotrons, like the Advanced Photon Source at Argonne, or the Diamond Light facility that John Todero was telling us about using for COVID pharmaceuticals yesterday. In all of these settings, and many, many more, we have both a wealth of data as well as physical information. And the question is how to best integrate the two. Okay, so let me put a kind of real concrete spin on this in the context of a CT scan. So who here has ever had a CT scan? Okay, a few people. So the basic idea is that you're lying there in the scanner and it's shooting x-rays through your body. And then out the other side, you get measurements of how much of that x-ray energy was absorbed. So this white line is an absorption profile. And I'm plotting that same absorption profile here where black means low absorption and white means high absorption. And as you lay there, this whole system rotates around your body and you measure an absorption profile for each angle, and they're getting plotted over here on the right. So the raw data collected by this system is this sinogram here. And what computed tomography does is it takes that sinogram and uses computers to reconstruct the image. So a few years ago, people started asking, well, is it possible to use machine learning to do this image reconstruction process? And if so, maybe we could get more accuracy, maybe we could get methods that are faster. There were a variety of potential benefits. And early efforts just took a whole bunch of sinogram brain image pairs and used it to train a somewhat generic neural network. And they got results that looked promising, but it just took a huge amount of data. Oops. Okay, well, it took a huge amount of data, and there were two key reasons for that. The first is that, or I'm sorry, the one reason is that we were asking the neural network to do two key things. One, we were asking the neural network to learn something about the geometry of the brain images. What kind of structures were present? What made a brain image look like a brain image? And this is what we wanted it to learn. The other thing was we were asking it to learn about the relationship between the sinogram and the brain images. But this is something we already know, right? This is a complicated relationship. It takes a lot of data to learn, and it was totally redundant because we already had that information. And so what we wanted to be able to do is to sort of bypass learning something we already knew. Okay, so the question is then, could we design a neural network that we could train using training data, but which also incorporated our knowledge of this underlying physical model? And of course, I'm here today. So the answer is yes. And I think this is really cool because it allows us to not just hack around at random designing neural network architectures, but to leverage decades of accumulated knowledge in inverse problems, data assimilation, optimization, and more to really guide the development of these systems. So just to put a finer point on this, let's let X correspond to the image that we want to reconstruct, and Y is the sinogram. And we're going to say Y is equal to HX plus epsilon. And so our goal is to recover X from Y. And H here is going to represent the operation of the scanner. So this is our physical knowledge. And so now what we want to do is we want to design a neural network that's going to take in a sinogram and output a brain image that somehow uses that physical model H. Okay, so if we think about it, if we think about how people have designed algorithms for constructing these images in the past, what they would do is they would say, well, let's search over all the possible images and let's choose one, X, which first of all is a good fit to the data. So it adheres to the sinogram that I've observed and also uses my knowledge of that physics, uses H. And then secondly, we had a regularization function that says, this looks like a brain. And historically, people did things like they said, well, X should be smooth, or it should be smooth with some smooth boundaries. But the question was, could we actually get more sophisticated models of brain images using tools like machine learning? And in fact, we can use these classical ideas to help design new machine learning tools. So I've got some equations here for the experts in the room, but for the non-experts in the room, the ideas, the way that we would do this classically is really very simple. We'd have this iterative procedure where we'd alternate back and forth between two steps. In the first step, we take our current estimate of the image, and we just perturb it a little bit to be closer to the data and closer to the physics. And then in the second step, we take any errors that popped up in this previous step and we try to smooth them out and make things look a little bit more like a brain image. And we just go back and forth, try to fit the physics better, try to fit the structure of the images that we expect better. And we can even represent this as a block diagram at the bottom. So now if we want to design a machine learning system, we can very simply take that regularization step and turn it into a neural network. And we have a block diagram here that looks like alternation between data consistency blocks and neural networks. And we would say, okay, let's run this for say 10 different blocks and let's train the neural network. So at the output, at the very end over here, looks good and is a good fit to our training data. And this is effective because within this whole block diagram, I have these trainable components, but I also have these data consistency blocks that are reflecting my physical knowledge. Okay, so first let me just state that this works, has done a lot of good work in practice. So this is an example from an MRI challenge where people were trying to image knees. And in the MRI data space, you would collect different measurements in Fourier space. The key thing to note here is that more white means more data, and it means slower data collection, so more expensive. And so what we can do is we can train these networks to reconstruct these images with really high accuracy and with a lot of speed. And we can also use these learned tools to make it possible to actually acquire the data even more quickly with less expense and still get very, very high quality reconstructions. And this is something where Max Welling is actually an expert. There was a big competition around reconstructing these images, and Max won the prize in 2019. But in addition to this being practically useful, one of the reasons that I'm excited about it is the following. So I had these data consistency blocks, and we can think about them as super simple neural networks, where the weights in this network depend on my known physics. So when I put everything together, I've just got one giant neural network here, where some of the components I'm learning from my data. And those are the components that correspond to the geometry of the image, the stuff I don't know. And some of the components are fixed and a function of this known physics. And so instead of sort of just blindly figuring out how to leverage my physical information, I've designed, using optimization ideas, a new neural network architecture here that incorporates that physical knowledge. Okay. Another way that we can think about physics-informed machine learning includes something that we've heard several people mention. So we talked earlier about taking data and from that figuring out governing equations, but we can also think about the opposite of this process, where we have some kind of governing equations or models, and what we'd like to do is to figure out faster and less expensive ways to map that into simulations. And so we have seen lots of examples of people using things like physics-informed neural networks, some of the stuff Anima talked about yesterday with her Fourier neural operator, trying to do exactly this. And it's had great implications in things like weather prediction, other kinds of complex systems, fluid dynamics, and more. Another core challenge here is in something that Libby talked about on our first day. So she said one of the problems that she faces is what she calls the temperature reconstruction problem. We'd like to understand or know what the temperature is all over the globe so we can make better predictions and forecasts, but we only have sensors at certain locations. And so we need to fill in the missing pieces. And she said, it looks sort of like an image painting problem, which we sort of know how to do. But in fact, there's all kinds of physical constraints and processes underlying this that we should be able to incorporate in order to do a really good job at this temperature reconstruction problem. Okay, now, in general, I think the real power of these physics-informed machine learning tools is that they make these systems more robust and data efficient, and they also allow us to extrapolate beyond the domain of our training data. So if we're trying to think about climate forecasting, we don't have training data that reflects what our climate is likely to look like 50 years from now. And so typically machine learning is learning from example. And if we don't have any examples out there, then we're just not, machine learning won't get us very far. But by incorporating physical knowledge, we actually have a hope that we're going to be able to make good predictions in areas that are far from our training data. Okay, so the final thing that I want to cover here are advances in AI frontiers, things that have shown up across the board from all of our talks this week in physics and chemistry and biology and earth science. The development of new AI and machine learning theory and methods that are inspired by scientific settings, but which are going to have broad impacts across the board. Okay, so the first one that we've heard many people talk about is interpretable AI. I think that Libby talked about this as a step towards causality. Caroline said we're scientists at heart. We want to understand underlying mechanisms. This is not just about prediction. And even when we talk about discovering governing equations, this is really about trying to interpret what our machine learning systems are doing. And we've also seen some examples of people getting some kind of interpretation from their results. But I just want to emphasize that this is not by any means a solved problem. For instance, we could say, well, what genes are being used to predict some phenotype? And there we could maybe train a machine learning system and get some kind of interpretable answer perhaps to this. But we could also say, hey, I've got a whole genome and there are global interactions, long-range interactions there that are controlling how chromatin folds. And that's controlling what genes are being expressed, and that's what's controlling the phenotype. And none of our methods in interpretable or explainable AI are anywhere close to giving this kind of interpretability or explainability. And similarly in climate, we could say, like Libby did, well, which sea surface temperatures in what part of the globe are going to affect whether California gets extra rain? And that kind of question, we've got tools that are helping us answer. But if we say instead, well, what are the spatiotemporal interactions among sea surface temperatures, Madden-Julian oscillations, stratocumulus clouds, and landmass use that predict precipitation? Again, none of our existing tools in interpretable and explainable AI are yet capable of helping us answer these questions. Another thing that's arisen multiple times throughout our conference here is generative models for science. Things like generating different kinds of protein structures, generating climate scenarios, or even generating examples of particles interacting in a particle physics setting. And what I want to emphasize here is that while we've seen some really exciting advances in generative models for images and text, when it comes to science, there still remains some foundational challenges and opportunities. So when we think about trying to do generative modeling in science, we really have to think about how to leverage physical models, constraints, symmetries, and invariances like Fiala was telling us about yesterday with this really inspiring picture of different kinds of cat invariances. We also have to think about how to handle rare events like Aaron was talking about this morning. If I'm going to build a climate emulator and I just can't reproduce any hurricanes because I get really small errors without reproducing hurricanes, then I'm missing really important features that impact my ability to understand the underlying science. In addition, in science, we have huge variations in scale and resolutions, well beyond anything that we've seen with images and text. Another thing that I'd like to mention is uncertainty quantification. And this kind of harkens back to something I talked about earlier with interactive design of experiments. The whole reason that this was possible is that we were able to not only make predictions, but we were able to assess when we had high confidence and when we had low confidence in our predictions. And there's a lot of ongoing work in this space, ranging from Bayesian neural networks to conformal prediction to, oh, sorry, now I'm just drawing a blank. But there's a lot of space going on a lot of work going on in this space and a lot of open questions. What's the right balance between incorporating prior knowledge about our process and really capturing uncertainty in these super complex systems? We've also seen a lot of exciting examples about people trying to learn from simulations of weather and climate, simulations of black holes, simulations of molecules and polymers. This requires a lot of advances in AI. These are not solved problems. We need to understand things like distribution drift, because the distribution of the data coming from our simulators is different from the distribution of real world data. And if we don't understand how to transfer from one distribution to another, then we risk really being biased by our simulations in a potentially catastrophic way. We also need to understand tools like data assimilation and reduced order modeling. And these are things that have been around for a long time, but are not fully integrated into our AI and machine learning systems. And then finally, we need to think about things like active learning. If I've got a simulator and it's big and expensive, then what are the best simulations for me to run? How can I best use that resource? Finally, oh, no, not finally. I also want to just do a call out to graphs, and Max did a great job of describing many of the different applications in which graphs are an excellent way to represent scientific data, from representing molecular structures to representing organs, cellular, molecular, and genetic networks, to representing neural networks like David was describing to us in his talk, to even representing interactions among particles as we try to understand what underlying governing laws look like. I also want to make mention of efficiency. And this is something that really has not been discussed at this conference so far. But the fact is that when we're training large-scale systems, things on the order of ChatGPT, this is using a huge amount of computational resources. And this is worrying for a few different reasons. One is that I just care about the climate, and I'm worried about the carbon footprint of all of us trying to work at this scale. But in addition, we run the risk that only certain institutions are going to have the capabilities to build models at this scale. And if only a few institutions have these capabilities and they have their own set of incentives, then it's not clear exactly what that implies for the future of science. And so I think there's a real need to take the insights that we've gained from these giant models at scale and to think about now how to actually map them back down to things that are much more efficient, both in terms of data and in terms of computation. Okay. And I just also want to mention that especially when we have human-centric data, we have to be especially careful when thinking about things like privacy, transparency, fairness, and accountability. Okay, so we've seen these four kind of key pillars, areas of AI and machine learning that show up across the natural sciences and engineering. And these are the things that I really think investments in are going to have a multiplicative effect in multiple different disciplines. And one of the reasons why I think this, at least for me, was a really fun conference, because I was able to see how different ideas show up in totally different ways in different fields and see how people from different fields could potentially help each other. But underpinning this, we also have to think about this culture of scholarship that's going to support all of these research initiatives. and in particular, institutions that are enabling sustained interactions across disciplinary boundaries, sort of like the kinds of things we've been doing for the last 2.5 days here, but also through hiring and training mechanisms. They are going to ensure that whatever AI advances we have, we create are going to have a multiplicative effect across many disciplines. So what do we need to do? Well, part of this is about transforming the way that we train trainees. So when we talk about training domain scientists to use AI, they shouldn't be looking at this as a magic black box. They need to understand, what are the potential pitfalls? What are the potential biases? What are the risks that I run in trying to infer science from my using AI? And simultaneously, AI trainees cannot think about the sciences as nothing more than a source of cool data. They need to understand, what are the physical models, what are the constraints, what's the provenance of the data, and what are the questions being asked. So I think the Eric and Wendy Schmidt Foundation is really sort of leading the way in this kind of transformed traineeship with the Eric and Wendy Schmidt AI and Science Postdoctoral Fellowships. There's 7 of these across the world. One of them is here at the University of Chicago, and it's really kind of building up these kind of principles. In addition, things like the Data Science Clinic, led by co-organizer David Uminski here, is taking undergraduates and putting them on small project-based teams in order to work with real data scientists on real scientific data with some modest supervision. And so one example of this was some students working with the Deep Underground Neutrino Experiment, or DUNE, at Fermilab, and figuring out how they could use machine learning algorithms in order to detect neutrino events and classify them. And they gained a lot of valuable insight, and I think this is a great example of this co-trainee program. And then finally, we've got people here from the NSF today, and I think the NSF has also been doing a fabulous job here with their trainee programs in harnessing the data revolution, but also other programs throughout the country. They've really focused in an excellent way, I think, in trying to train people across disciplines to communicate and to work productively together. Okay. We also have a set of common institutional needs, such as robust, reliable, open source software and data for reproducible research. And this is another area where the NSF has partnered with universities like UChicago and MIT and the University of Wisconsin, as well as national labs like Argonne, in order to build systems like Model Gardens. This is a new project where we can publish and curate AI models, link them with data and computing resources, and make it easy for people to test and deploy these tools across different disciplinary boundaries. And then finally, we need to think about how academia, industry, and national labs should continue to interact and work together in this new era of AI and science. Each of these has unique strengths and benefits, but as we think about scaling up some of these machine learning systems, I think these interactions are going to transform, and by working together, we're really going to be able to advance these ideas as well as possible. And so finally, just to return to my core thesis, AI and machine learning are transforming scientific research. And hopefully I've given a nice overview of some of the foundational needs that we have on the AI and machine learning side that hopefully will really make a lot of the scientific discoveries and the moonshot ideas that we talked about at the beginning a reality for us all. So thank you very much.
Thank you, Becca. We have time for a few questions from the audience. You answered most of them, but
You know, it was an overview too.
Hi, Rebecca. It was beautiful. I'm Laura Gagliardi. I had just a comment on the last part when you said be able to contribute to this because they have access to certain resources, but isn't it true for every aspect of science and engineering and advancing knowledge? So don't you think that in a way this makes things more democratic than other approaches to novel discoveries?
Yeah, I guess what I had in mind was, if we think about some of the big shared physics facilities, like the Large Hadron Collider, then you're right, there's only one Large Hadron Collider, but there is this community of scholars that's working together to decide, well, what are the highest priority experiments to run on those systems? And so the academic community is deeply engaged in that process. In contrast, if we've got large scale AI capabilities only at a small number of, say, for-profit institutions, then that's a different thing, right? That is less democratic. They've got their own set of incentives. And not that that's bad. And then, Max told us a bunch of the stuff that Microsoft's doing, and I thought it was very compelling and very exciting. But it is not democratic, right? And so it does have, I think it's worth thinking about what that future looks like.
Anyone? Then, okay, Fiala first.
Hi, great overview. Thank you. I was curious at the end that you didn't mention the need for computation. I fully agree that we have to develop a workforce that's really interdisciplinary, and it feels like there are steps going in that direction. But what to me feels really problematic right now is that we're starting to develop a workforce and they have no computational resources to develop new tools. You have a great fellows program. We have one at MIT. Being able to support those fellows with the resources they need on the computational side is a real challenge.
That's a great point, right? So I really did kind of focus beyond the scaling on what these foundational challenges are. But you're right, when we think especially about training, not being able to train on these large scale systems is affecting sort of the preparedness of our students and postdocs. And so that's another kind of challenge associated with having the computational resources at scale concentrated in a small number of institutions.
Yeah. Thank you, Becca. I wanted to thank you for, spearheading and really bringing all of us together. And and of course, the Pritzker Foundation for supporting this. So, what we were talking yesterday of how to take this forward, right? I wanted to discuss with everybody here that because I think this can be a core community to further enhance the collaborations across areas, right? And so we should continue to do that. I think I would propose, having a mailing list, keeping us in touch, but also maybe like monthly or biweekly have students present because, we had a small number of posters, but there's just so much work that, in this group that is happening and it could even be something that, people get inputs, right? Especially, so at Caltech, what we did was before the pandemic, we had a very active group that we want to, bring it back where machine learning students would just meet casually and have like volunteer their time and everybody could come in from other domain sciences, just present their problems, get some inputs, right? Get started on using machine learning. And so here it could be much more focused where people who are working on targeted problems can announce that they need help or we have like regular meetings where just, everybody meets on Zoom and, gives comments and feedback. I think, but it would be great to also hear from others if there are other ways we can continue what we've started now.
Yeah,
Thank you.
These are great points. Thanks, Anima. I'm glad you mentioned these things.
There's a question here.
Yeah, hi. I was wondering, do you have any thoughts? I'm kind of putting you on the spot here, but do you have any thoughts about, how do you organize people that are doing very, very different types of science in a way that, there's some benefit to be gained by leveraging, that common effort and whatever possible overlaps there are?
Yeah, I mean, it is tricky, right? Because we're all busy and we've got a lot of demands on our time. And at the same time, when I come to things like this, I personally gain a lot. I hope my students have gained a lot. And so I think these kind of convenings are useful. I think other structures, centers and institutes like the Data Science Institute, where there are regular mechanisms and resources to bring people together can be really useful. So things like shared postdocs that are being co-trained, shared students, or even faculty hiring initiatives that can span traditional disciplinary boundaries and attract people who want to be working at that interface regularly. I think those can all be really transformative for an institution.
Let's thank Becca once again. And
Yes.
before we do that,